second part of the canonical mapping, we firstly define the concept isomorphism. Isomorphism. The mapping is said to be an isomorphism if it is both 1 on 2 and preserve the structure. That is the definition of the isomorphism. Isomorphism, it is always the bijective mapping and which preserve the structure. For example, here we have the metric space x comma d, that is a metric space, and y comma d star, this is another metric space, and T with the mapping from x to y, such that T is both 1 on 2 and for all x comma y belongs to capital X, D of x comma y, because here x and y both are the element of capital X. As x and y both are the element of capital X, therefore their images, that is Tx and Ty, they are the elements of capital Y. On x we have the metric D, on y we have the metric D star. Then here in this structure X, the metric is D, therefore here we take the D of x comma y. Here Tx and Ty, these are the element of y. On y we have the metric D star, therefore here we are taking D star of Tx comma Ty. If D of x comma y it is equals to D star of Tx comma Ty, that means the mapping T preserve the structure, and therefore if the mapping T which is from x to y, which is 1 on 2 and preserve the structure, then we say that the mapping T is an isomorphism and x is called as isomorphic to y, or y is isomorphic to x. In this way, this is the definition of isomorphism between the metric spaces. Now after this isomorphism between the two metric spaces, now if we have the two vector spaces, in the vector space we have the addition and scalar multiplication. Here we take the two vector spaces x and x tilde, be any two vector spaces, and capital T with a mapping from x to x tilde, such that T is bijective. Bijective means injective and surjective. Injective means 1, surjective means onto. The mapping T from x to x tilde is both 1 and onto. And now x is a vector space, therefore it is closed with respect to addition and scalar multiplication defined in this space. In the same way, x tilde is also a vector space, therefore it also have the addition and scalar multiplication. Now here T is the mapping which is from x to x tilde, both 1 and onto, and also satisfy the another condition that for all x comma y belongs to capital X and alpha be any scalar, T of x plus y, that is equals to Tx plus Ty. In the same way, T of alpha x, it is equals to alpha Tx. That means here this T preserve the structure. Then we say that the mapping T is an isomorphism. That means here T is 1 on 2 and it preserve the structure, that is the linear operator, and therefore here T is also called as a linear operator. Here we say that x tilde is called isomorphic with capital X, and x tilde are called isomorphic vector spaces. Now here we define the isomorphism between the two vector spaces. In the same way we define the isomorphism between the norm spaces. We consider any two norm spaces like this. X be the norm space with the norm x and y is the norm space with the norm y. And if T is the mapping which is from the norm space x to y, which is both 1 and onto. If this T preserve the norm, then we say that T is an isomorphism. In this way we define the isomorphism. Now here we have to show that our canonical mapping, it is from x to x star. It takes the element small x belongs to capital X and here we are getting the element c of x. C of x, it is nothing but the gx, that is a linear functional on x star. This is our canonical mapping. Now here we show that this canonical mapping is an isomorphism. To prove this here, firstly we show that this canonical mapping is 1 1. To show that the canonical mapping is 1 1, here we take any two element of capital X and we show that if their images are equal, implies the points are equal. Then we get that C is 1 1. And therefore, let's start with Cx equals to Cy. As Cx equals to Cy, it means that it is Cx equals to Gx, and Gx is nothing but Gx of f for all f belongs to x star. And therefore, Cx equals to Cy implies that Gx equals to Gy, and it is nothing but Gx of f, it is equals to Gx, sorry, not Gx, it is Gy of f for all f belongs to x star. Now, but Gx of f, it is equals to Gy of f, implies that Gx of f is equals to Gy of f for all f belongs to x star, but it is nothing but f of x, it is equals to f of y, and it is true for all f belongs to x star. That means for any linear functional, on x, their images are equal for any f, and it is possible only when the points are equal. And therefore, we start with Cx equals to Cy and we get that x is equals to y. That is for any x comma y belongs to capital X, images are equal, C of x equals to C of y implies that x is equals to y. And this implies that the mapping C, which is from x to x double star, it is 1 1. Now we also prove its linearity, that the mapping C is linear, and therefore here as C is the mapping from x to x double star and this mapping is 1 1 as we prove, this implies that the mapping C, which is from x to, now I am taking the range of C, that is the script R of C. Now it is a subset of x double star. Here we observe that the mapping C, which is from x to its range, this mapping is always an onto map. And as earlier we proved that the mapping is 1 1, therefore the mapping C, which is from x to script R of C, it becomes both 1 1 and onto, and that means the mapping C is canonical mapping from x to script R of C. It is a bijective mapping. Now we prove that C is structure preserving. For this here we are taking any 2 point of capital X. That means we take the point x comma y belongs to capital X, and here we are taking alpha b any scalar. Then C of x plus y, that is equals to C of x plus y of f, and it is equals to, by using the definition, it is equals to gx plus y of f. It is equals to f of x plus y, and as f is linear, it is equals to f of x plus f of y. Again, f of x is written as gx of f, f of y is written as gy of f. Now gx of f, it is nothing but cx of f plus it is cy of f. That means we start with that c of x plus y, it is equals to c of x plus y of f, and it is equals to cx of f plus cy of f, and it is equals to cx plus cy. That means c of x plus y, it is equals to cx plus cy. In the same way, we also show that c of alpha x. Now by definition, it is equals to c of alpha x of f for all f belongs to x star. It is nothing but G alpha x of f for all f belongs to x star. It is equals to f of alpha x. F is linear and therefore it is equals to alpha f of x. It is equals to alpha. It is equals to gx of f, and that is equals to alpha cx of f. It is alpha c of x. That is c of alpha x. It is equals to alpha c of x. This implies that the mapping C from x to script r of C is 1 1 on 2, and as we get the two results, that C of alpha x is equals to alpha C of x and C of x plus y, that is equals to Cx plus Cy. From this here we get that the mapping C bijective as well as the structure preserving, that means linearity, and therefore the mapping C, which is from x to script r of C, it is an isomorphism. That means here the mapping C from x to script r of C is an isomorphism. It means that x is isomorphic to script r of C, and script r of C, it is a subspace of x double star. It means that we say that capital X is isomorphic with a subspace of a vector space X double star, because here X is isomorphic to script r of C. Script r of C is a subspace of a vector space X double star, and it implies that C is isomorphic to a subspace of X double star, and this implies that capital X is embeddable. It is embeddable in X double star. Because it is embeddable in X double star, because capital X is isomorphic to a subspace of X double star. As X is isomorphic to a subspace of X double star, it means that capital X is embeddable in X double star. In this way, from the canonical mapping C, which is from X to X double star, we show that this mapping is 1 1. After that, if we are taking the range of C, that is the script r of C, then this mapping is onto. We also show that this mapping preserve the structure, and therefore C is an isomorphism from X to script r of C, and therefore here we say that X is isomorphic to script r of C. Script r of C, it is a subspace of X double star, and therefore we are getting that X is embedded in X double star. Now after that, here again, if this script r of C, it is equals to X double star, if this range set, it is equals to X double star, then in this case the mapping C, which is from X to X double star, this is both 1 1 on 2, and in this case we say that the capital X is algebraically reflexive. In this case we get capital X is algebraically reflexive. When script r of C is equals to X double star. Otherwise, when the script r of C, it is a subspace of X double star, then in this case we say that capital X is embedded in X double star. But when this range set, it is equals to X double star, then the mapping C, which is from X to X double star, is both bijective, and in this case we get that capital X is algebraically reflexive. This is about the canonical mapping.